Hello, welcome back. Now we're going to look at global maxima, global minima. Basically, global means where is the highest point on the entire graph, the lowest point on the entire graph. Okay, so we're opening our world up, bump. I know, it's sad. I've been alone way too much lately. Okay, so anyway, sometimes they're called absolute extrema, absolutely the highest point, absolutely the lowest point. All right, so let's talk about this. The thing that's different now is if we have endpoints, they can be a global max or global min. Okay, remember local max and min cannot be at endpoints, but global can. All right, so first one, linear. Is there a highest point on the graph? No. So there are no global extrema here, right? The range is all real numbers, so that can happen. There's no local max or min either. All right, how about this parabola? We have a global max, right? Let me do this. Okay, this is a a global minimum point. Okay, it's also a local minimum. Okay, but there is no global max because that continues going on and on. All right. So not always guaranteed that we have both or either. All right, here's kind of a cool function. This is actually the graph of a rational function. Believe it or not, it does have a horizontal asymptote, but it doesn't have a vertical asymptote. All right, so is there a highest point? Yes, there is. So this would be the global maximum. And we have a global minimum, which is also a local minimum. Highest and lowest point. Okay, here's an interesting graph. It's part of a polynomial function, but notice how we have endpoints. Okay, so I have an end point here, end point here. All right, so if I'm looking at the graph, where is the highest, absolutely highest point? Right here. So I actually have a global maximum at an end point. Okay, where is the absolutely lowest point on the graph? Down here. Okay, so this is a, let's write this down. This is a local minimum. It's also a critical point, right? Horizontal tangent line. And it is a global minimum as well. Okay. This point here is a local maximum and a critical point. But it is not a global max or min. And this end point here is neither. Okay? So you can see that the point here is that a global maximum can occur at an end point, or it can occur at a local minimum or a critical point in the interval. Okay, or local maximum. All right, how about these two graphs? Okay, here's the one that I was talking about before. $1 million if you can give me the name of the functions graphed. All right, so this is e to the x, or looks like, I guess we should say, and this is natural log, whoops, that looks weird combining those, natural log of x. All right, so do they have any local min or max? No. Do they have any global max or min? No. So these have no global extrema. So that can happen. Now, if we restricted those domains, we could have a global max or min. But if we look at the domain of the function, which this is all real numbers, this domain, and this domain, remember, is 0 to infinity. Okay? So, how do we find these global max and mins without relying on a graph? All right. First piece of information that is very helpful. If a function has a global max or min, it will occur at a critical point, right? Critical point, or at an end point, okay? So global extrema can occur at end points, all right? If a function is continuous on a closed interval, here's the difference. If we close the interval, then it will have both, okay? We got to make sure that it is continuous, meaning there's no breaks in the graph, okay? We'll have both of those, okay? If a continuous function has only one local maximum or one local minimum, then that will be the absolute, or excuse me, the global maximum or global minimum. So this kind of pertains more to functions that are not on a closed interval typically. And the last one, it's possible to have 2 points that are absolutely the highest, or more than one, or absolutely the lowest. So you might have more than one global max or global min. Dun, da, 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 I'm not ruining the surprise. Here's an example. Whoops. Here's an example of a polynomial function that would be even degree, right? It's got to be even degree because both sides are down. Okay. So this one does have global max. Those are the highest. So global maximum occurs at 2 points. All right, so how do we find these? Let's start with just talking about a function without restricting its domain. So, polynomial function, okay? I know that the domain is all real numbers, okay? I know that because this is degree 3, that its range is all real numbers also, right? Odd end behavior goes up to the right, down to the left. So if I look at the graph, here it is. Does it have any absolute maximum or minimum? No. So it has no I keep saying absolute, sorry, that's because when I taught Calc 1, that's what we said. All right, sorry, no global extrema. No highest or lowest point, okay? But if I restrict the domain, okay? If I restrict the domain to a closed interval, closed means includes its endpoints. This is the way we wrote it in college algebra, but in our book, we're going to see it written like this with inequality notation. So know that it is the same. Basically saying, if we're only looking at the part of the graph between -4 and 5, including those endpoints, okay? If we restrict it, so if you think about it, let's go up here. If I think about this and I chop it off at -4, and what, 5, was that my other one? Okay, and I just look at this part of the graph, there is a highest and a lowest point. Okay, so what we want to find is, what are those points? Or is it this point? I don't know. Okay, so what's the location of those highest and lowest points on that part of the graph? Okay, so how can we do that without relying on the graph? Well, we know that the global max or min will occur at critical points in the interval. So I need to find the critical points and then choose those that are in that interval between -4 and 5. All right, critical points, what do we need? First derivative. So first derivative is critical points are values that make the first derivative equal to 0. Okay. Factoring. Once again, first thing you should look for is greatest common factor. Even if it's a constant, it makes life much easier. So I have a factor of 3 that I can pull out. So divide everything by 3. And now here's one of our trinomials that if it factors into 2 binomials, kind of the reverse FOIL method. Multiply to be -3, add up to be -2. So it's going to be 3 and 1. So it's going to be x plus 1, x minus 3. All right. So set each factor equal to 0. This will never be 0. So it does not give me a critical value, critical point. So this one's going to give me x equals -1, and this one's going to give me x equals 3. Okay. Are both of these in the interval? So these are both critical points. Is -1 in this interval? Yes, it is between -4 and 5. Is 3 between -4 and 5? Yes. So these are critical points. They are in the interval -4 to 5. So they could potentially be a global max or min. Okay? So there is no testing in the derivative here. It's basically, these are x coordinates of points on the graph. So what's their y values? Okay? I want to know which points have the largest y values, which of those x values. Okay? So that's what we're looking for. So we substitute the critical points. Substitute the critical points that are in the interval. That's a key. Huge. Critical points that they must be in the interval into the original function. You're trying to find the y coordinate because you want the smallest y value and the largest y value. Okay, those will be the highest and the lowest points. Okay, so what I do is I think about my interval. I'm going from -4 to 5. So I've got my endpoints. So I have -4, and I've got my other endpoint, which is 5, and then I've got my critical points. So I've got my critical point, which is -1, and critical point, which is 3. Okay, so I like to go left to right. Makes better sense to me. All right, substitute those into the function. So if I plug -4 into this function here, I get -61. If I plug -1 into the function, I get 20. If I plug 3 into the function, I get -12. And if I plug 5 into the function, I get 20. Okay, so you're looking for the largest y value and the smallest y value. Okay, let's go with the global minimum. Smallest function value. Which of these are the smallest? -61. Smallest. Okay, so that tells me then that I have a global minimum. The point on the graph is -4, -61. So if I look at that part of the graph, that's going to be the lowest point. Maximum. Well, what have I got going here? 20, and 20. So here I have two places where I have the largest y value. Okay, so that means I have two global maximum points. And those are at the point -120 and 520. So what am I seeing that's happening here? I'm seeing that my global minimum is at an end point on the graph, which is totally fine for global. And my maximum, this one is at a critical point, and this one is at an end point. Okay, are you ready? Drum roll, please. Do 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 do. Here we go. I'm sorry, but I gotta entertain myself. I'm standing here by myself, talking to myself in a room. The security guard just knocked on the door and scared the crap out of me. Anyway, all right, so we can see then the results of our work. So we can do it without relying on a graph. Pretty cool. So